All right, so simplifying trig identities. There's a bunch of things you want to make sure that you have memorized to be able to like replace things. That's what you're doing a lot of times in simplifying these identities, is replacing them with things that can be combined or canceled or whatever it happens to be. So it's important to remember things like cosecant is 1 over sine, secant is 1 over cosine. Cotangent is 1 over tangent, but I'm going to actually try to remember cotangent as cosine over sine, because a lot of times you want to get everything to be in terms of sine and cosine because it'll be easier for you to combine together. Tangent is sine over cosine. There's something called the Pythagorean identity, which really goes back to the unit circle with the fact that like x is cosine, y is sine, and you'll eventually be able to figure out that sine squared plus cosine squared equals 1. So you'll have to memorize this. Two alternative forms of these identities. If I were to subtract sine squared from both sides or subtract cosine squared from both sides, I get 1 minus cosine squared is sine squared, and 1 minus sine squared is cosine squared. Okay, for now, just keep this on the top of your page as you do the work in these problems, because you're going to be using these to sub in to the expressions below. You'll know you're done when you get everything down to a single term. So that single term could be a 1, a sine, a cosine, a cosecant, a sine squared. It all depends on what happens as you work through your problem. So, for example, as you get into number 1, it says secant of theta times the sine of theta. The first thing you want to do is get everything to be in terms of sine and cosine. So, secant can be replaced with 1 over cosine. Sine of theta I'm not going to replace with anything. I'm just going to make that sine of theta over 1. The way fractions work, you multiply the numerators, you multiply the denominators, and then you can reduce sine over cosine, as we said before, to be tangent of theta. So you now just found out that secant times sine comes out to be tangent. And just so you know, the idea of an identity is that if you plug in a value for theta, let's say 30 degrees, into the original problem and into the final answer, you should get the exact same answer for any value of theta that you plug in. Okay? Let's get on to number 2. So cosine theta times tangent of theta. Cosine theta is already in terms of sine and cosine, so I'm just going to put that over 1. Tangent of theta can be replaced with sine over cosine. Okay, so now it's nice, similar back to like rational expressions. These cosines can be canceled, and I'm left with sine of theta over 1, which is really just sine of theta. With number 2, tangent squared minus secant squared. I'm going to do the same thing I did before, where I replace it to be in terms of sine and cosine. So tangent squared is actually going to turn into sine squared over cosine squared. Okay, because tangent is sine over cosine, and squared, I have to square the top and bottom. Secant squared, just like secant is 1 over cosine, secant squared is going to be 1 over cosine squared. Okay, so now you'll notice that I have 2 separate fractions, but thankfully they have a common denominator. I can actually add these terms together. So this becomes sine squared theta minus 1 all over cosine squared. Now this is a little bit tricky, this one, because I'm supposed to see something like 1 minus sine squared, and I see something like sine squared minus 1. So what I'm going to do is I'm actually going to factor out a negative 1 from this. Okay, when I do that, I'll have negative sine squared plus 1. Okay, I'm just going to rearrange the order of that a little. That becomes negative 1 out front. This becomes 1 minus sine squared all over cosine squared. And this is where we use one of those Pythagorean identities. 1 minus sine squared is the same thing as cosine squared. So I'm going to get this negative 1 stays out front. This whole thing, 1 minus sine squared, gets replaced with cosine squared. Okay, in my denominator I have cosine squared. These will cancel, and I'll be left with just negative 1. Okay, so that one's a little tricky, especially at this point with the factoring out the negative 1. But most of the time, you'll have 2 fractions, combine them together, use your Pythagorean identity or your reciprocal and quotient identities, reduce, okay, simplify and reduce, and eventually get down to 1 single term. Okay, so I think you'll find that this last one, sorry, number 4, actually is probably going to be even easier than number 3. I have some parentheses, so just like I would during an equation, I'll distribute to get rid of those parentheses. Cosine theta times secant theta minus cosine times cosine, which is cosine squared. Let's put everything in terms of sine and cosine. This is cosine theta over 1 times 1 over cosine minus cosine squared. These cosines will cancel. When things cancel, they don't cancel to be 0, they cancel to be 1. So I have 1 minus cosine squared. Go right here to my Pythagorean identities. 1 minus cosine squared is sine squared. Now that I'm down to one single term, that's how you know that you're finished. So again, get everything in terms of sine and cosine, use reciprocals and quotients to cancel things out, use Pythagorean identities if you have two fractions to combine together to try to replace things, get down to one single term. All right, so solving first degree trig equations, I will point out it's going to be really important that you make sure your calculator is in degree mode for this, because you're going to be using like second sine and second cosine and second tangent, and if you have it in radian mode, you're going to get totally different answers. Okay, so it says solve for all values of theta in the interval from 0 to 360. Notice that it mentions it in degrees. That means you leave your answers in degrees. And I say answers because most of these will have at least two answers. So the first thing you want to do with most of these questions is make an ASTC chart. Okay, don't worry about the fact that sine is rad 2 over 2. Worry about the fact that sine right now is positive. Which two quadrants can sine be positive? In the first quadrant and the second quadrant. Reference angles are always done with respect to the x-axis. So draw your reference angles back to the x-axis, and now we're going to use our calculator to figure out the reference angle, which is eventually going to give us angles in the first and second quadrant. That'll be our solutions. So in my calculator, to work backwards from something like the sine of theta is rad 2 over 2, I'm going to hit second sine, rad 2, make sure you end that, divided by 2, and I get a reference angle of 45. Now the thing is, 45 might not always be a solution. It depends on what quadrants that we're in. Think about your rotations. This is 0, 90, 180, 270, back to 360. So what are these angles really? Well, thankfully in the first quadrant, our reference angle is our actual angle. So one of our solutions is 45 degrees. But the second solution is in the second quadrant with a reference angle of 45. How much did I rotate to get to this point right here? Well, think about the fact that to rotate all the way to here, I'd have rotated to 180, but I'm coming back 45 degrees. So I do 180 minus 45, and that tells me in this quadrant, this is really an angle of 135 degrees. Okay, whoops, not 1350. Okay, and that is both solutions that satisfy this trig equation. So take a look at number 2. Sometimes I have to do a little work to get the sine or the cosine or the whatever by itself. So I'll divide both sides by 2. This gives me cosine theta equals negative 1/2. So again, I'm going to make an ASTC chart. Where is cosine negative? Cosine is positive in the first and fourth quadrant, which means cosine is negative in the second and third quadrants. Reference angles are done with respect to the x-axis. Now when you go to type this in your calculator, you're going to want to just type it in as second cosine of 1/2. The negative is there for you to figure out the quadrant, but you don't need that when you're finding the reference angle. So second cosine of 1/2 gives me a reference angle of 60, but 60 is not going to be one of my answers this time. We're talking about 60 in the second quadrant and 60 in the third quadrant. So think about, how did you rotate to get to this point? You're 60 degrees short of 180, so 180 minus 60 would give me an angle of 120 here. And in the third quadrant, you've got 180 degrees plus an additional 60, so that's 240 degrees. Okay, so that's my solutions, 120 and 240. And if you ever want to check yourself, plug in 2 cosine 120, you'll see negative 1, or 2 cosine of 240, and again, you'll see negative 1. Okay, so take a look at number 3. It's a little more solving. So I'm going to minus this radical from both sides. Don't worry about the radical being there. It still will work out to be a nice value. Divide both sides by 3. So this gives me tangent of theta equals negative rad 3 over 3. And now I begin that ASTC chart process. Where is tangent negative? That's really important. Well, tangent is positive in the first and third quadrants. Tangent is negative in the second and fourth quadrants. In your calculator, you don't want to do second tan negative, okay? You want to just do second tan of the fraction to get the reference angle. So second tan rad 3 over 3 comes out to be 30 degrees. Okay, so now again, 30 is not going to be one of my answers in this case. You're talking about 30 in the second quadrant. So that's 180, take away 30. This is an angle of 150. And in the fourth quadrant, that's 360 minus 30. So that would be an angle of 330. Okay, so think about the values that should be in those quadrants. And hopefully the values that you're getting as solutions make sense to be in those quadrants. If it happens that you have a reciprocal function, it's mostly the same stuff with just a flip at a certain point, and then everything else will still be the same. So you still want to get it so that all of your variables are together, all of your numbers are together. So I want to try to get secants all to one side, numbers all to the other side. So I'm going to minus 3 secant theta from both sides. Okay, and I'm going to minus 3 from both sides. So on the left-hand side, you'll end up getting 1 secant theta, which is just secant theta, equals 1. All right, this is where the flip comes in mind. You're going to flip both sides of this expression, okay? Secant flips to become cosine. Well, thankfully, 1 still flips to be 1, but if that had been 1/2, it would become 2 over 1, or 1/3, it would become 3 over 1, or something like that. Now, cosine equals 1 is a little bit unique. It's not the same as when you have a half, or rad 3 over 3, or rad 2 over 2. This is not one you're going to get from an ASCC chart. This is actually going to be something that comes off of the points on the unit circle. Okay, so let's make our points on the unit circle. Okay, a cosine value, remember CVS, is an x value. Where do we have an x value of 1 means where did we move to the right 1 unit? That is this point right here. Okay, that's the point 1, 0. That's my cosine is 1. There's no other place where my x coordinate is going to be 1, so this would be 0 and 360 as my solution. Now, what might be a little bit of a better option, actually, this is what I do in my classes, if you sketch a basic cosine curve, where is cosine equal to 1? It's right here at the top at the beginning of my curve and at the end of my curve, except you just want to make sure that it's in degree form for these answers. In the next section of things, that's when you can start to leave your answer in radians. So if you look at question number 5, you're actually doing the same stuff you just did before, except at the end, you might have to convert your answers into radians. Because of the fact that it says 0 to 2 pi, you convert your answers to radians at the end. Okay, that means you'll times them by pi over 180. Okay, so I start getting sine of theta by itself. Add radical 3 to both sides. So I have 2 sine theta equals radical 3. Divide both sides by 2, so I get sine of theta equals radical 3 over 2. Okay, we're making our ASCC chart, just like we did in all of our previous problems. Sine is positive, so that will be in the first and the second quadrant. Again, reference angles with respect to the x-axis. So I'm doing second sine of radical 3 over 2. Gives me a reference angle of 60. Okay, notice how it's always coming back to 30, 45, or 60, or the unit circle. In the first quadrant, that will be an angle of 60 degrees. And in the second quadrant, that will be an angle of 120, 180 minus 60. You're not done, though, with 60 and 120. Convert them to radians. So times them by pi over 180. This comes out to be pi over 3, and this comes out to be 2 pi over 3. So my solution set should be pi over 3, comma 2 pi over 3. Okay, you just have to do that one extra step of converting to radians. All right, so solving second-degree trig equations is essentially going to be solving quadratic equations along with what we were just doing with our first-degree trig equations. So a lot of times what will make your life a little bit better when you start to do these problems is to maybe turn it in terms of like x or u or whatever you want it to be. So for here, let's start with this first one and we'll say, let x equal sine of theta. Okay, make that clear so at the end you know that you're switching back to sine of theta. That means that this equation is really going to be x squared minus 1 equals 0. When you look at it like that, it's probably a lot easier to be able to think of like how do you handle that as a quadratic? Get it equal to 0, take the square root, or factor it with dots, whatever way you want to do it. So I'm going to factor x squared minus 1 to come out to be x plus 1, x minus 1. You're going to start solving this. Okay, so I get x plus 1 equals 0, which gives me x equals negative 1, x minus 1 equals 0, which gives me x equals positive 1. And here's where the big difference is between solving quadratics and solving these trig equations. You have to go back and replace x with sine of theta. So this is saying sine of theta equals negative 1, and this is saying sine of theta equals positive 1. I think the easiest thing to do is to make a basic sketch of a sine curve. Okay, and use that when you have situations when sine or cosine equals 1, 0, or negative 1. Okay, you could also use the unit circle, that's totally fine, but that's basically what this graph is a graph of the unit circle points for the sine values. So where is sine equal to negative 1? This would be at 3 pi over 2, which is also known as 270 degrees. Where is sine equal to positive 1? That's right here where I would have pi over 2, which is also equivalent to 90 degrees. It's saying answer between 0 and 360, so my solutions would be theta equals 270 degrees and 90 degrees. Okay, so in the second one, I'll start with the same thing. Split this to make it a little easier to see. I'm going to say let x equals cosine theta. Oopsies, I think this is supposed to be a cosine. I apologize. Okay, so as I set this up, this is going to be 2x squared. This is going to be minus x minus 1 equals 0. I'm replacing cosine of theta with x. Notice I have, unfortunately, a tricky trinomial. So you can either do tricky trinomial factoring or you can do it with quadratic formula. It's totally up to you. I'm going to do tricky trinomial factoring. So remember, with tricky trinomials, you multiply your first and last numbers. That becomes your m. Your middle term is your a, which in this case is negative 1. You keep your first term exactly the same, you keep your last term exactly the same, and you split your middle term. How do you find things that multiply to 2 and add up to negative 1? That would be 2x and 1x. Because they're opposite signs, they multiply to a negative, they're opposite signs, and the larger number, which is the 2, gets the negative, so then the 1 gets the positive. You're now going to GCF each half of the expression, so factor a 2x out of these first terms and a 1 out of the second terms, and now you're going to factor out an x minus 1 from each half of this expression, so you'll be left over with 2x plus 1. So now you're going to split, and you're going to solve each of these smaller expressions. So x minus 1 equals 0 would give you x equals 1. 2x plus 1 equals 0 would give you 2x equals negative 1, or x equals negative 1/2. Once again, you're not finished though when you get to x. X is really cosine, so you have to replace these both to be back in terms of cosine. So I'm going to move up over here because I'm running out of space. So I have cosine of theta equals 1, and I have cosine of theta equals negative 1/2. Cosine theta equals 1 is going to be a unit circle value because 1, 0, or negative 1 always comes out to be a unit circle value. Where is cosine equal to 1? It's at the top of the cosine value, at the cosine curve. This is 0, this is 2 pi, and that's why this comes out to be 0 and 2 pi. Okay, so, or 0 and 360, I should say. When cosine of theta equals negative 1/2, this is when you're going to use the ASTC chart. So cosine is negative, which means it has to be in the second and the third quadrant. Reference angles with respect to the x-axis. Remember, when you type in your calculator, second cosine of just regular 1/2. Whoopsies. Okay, that way you get the reference angle, so 60. In the second quadrant, 180 minus 60 is 120. 180 plus 60 is 240. So your full solution set is 0, 360 in the first part, 120, 240. Okay, and again, if you want to check any of these answers, you take any of these and you plug them back into the original equation, and they should make a true equation. So when you get into ones where you have to solve and put it in radians, pretty much it's the same stuff you did before, except at the end you're going to have to switch it back to be in terms of radians. So times each of these values by pi over 180. So I'm going to start with my let statement. Let x equals cosine of theta. So then I rewrite this with x in there. 1 plus x equals 2 times 1 minus x squared. So I'll distribute to get rid of that parentheses. Okay, bring everything to one side, minus x, minus 1. Put it in descending order. So I have a negative 2x squared, a positive x, a minus 1. I don't really want to factor with a negative 2x squared in the front, or really a negative in the front, so I'm going to times everything by negative 1. So this becomes 0 equals 2x squared minus x plus 1 equals 0. So actually you're going to see a lot of similar stuff to what we had done in that previous problem where we ended up multiplying things to a certain number. I think actually this is incorrect. This should really be a minus. Okay, well, you know what? Let's just skip this question. Okay, because you can see everything you need to see in terms of factoring with tricky trinomials. Let's just say that we had to solve for the previous problem, like number 2, except we had to do it on the interval from 0 to 2 pi. Okay, so let's say it was this problem, 2 cosine squared theta minus cosine theta minus 1 equals 0. Okay, and we got our solutions as 0, 360, 120, 240. What you'd have to do if you see it's between 0 and 2 pi is to convert to radians. So I would still have 0. Okay, obviously that's not going to change when I multiply by pi over 180. But if I take 360 and I convert that to radians, 360 times pi over 180 is going to come out to be 2 pi. Okay, 120 times pi over 180 is going to come out to be 120 divided by 180. Comes out to be 2 pi over 3. Okay. 240 is going to be 4 pi over 3. And that's the only additional step you'd have to take in addition to what you did in question number 2 if you had an interval that said 0 to 2 pi. Okay, so if it just says 0 to 360, you leave it in degrees. If it says 0 to 2 pi, you convert your final answers into radians. So number 4 is the last one, and this one's a little interesting with regard to factoring because you have more than one trig function in that expression. So what you're going to do is you're still going to factor, but you're not going to be able to do any replacement with x or anything like that. So if you notice there's a sine of theta in each half of this expression, I'm going to start by factoring out a sine of theta. If I divide sine of theta into each of these halves, I'm left over with 1 minus 2 cosine theta as my second factor. Now that these are factored, now I can pretty much split them and solve each one of those factors. Sine of theta equals 0. 1 minus 2 cosine theta equals 0. Sine of theta equals 0, you're going to use your basic sine curve. Where is sine equal to 0? At 0, pi, and 2 pi. And actually, since we want radian values this time, I'm going to leave it as 0, pi, and 2 pi. For the next one, I'm going to bring 2 cosine theta to the other side. So I have 1 equals 2 cosine theta, divide by 2 on both sides, and I have 1/2 equals cosine theta. This is where you're going to be using the ASTC chart. Cosine is positive in the first and fourth quadrant. You type second cosine of 1/2 in your calculator to get a reference angle of 60. Thankfully, in the first quadrant, 60 is our actual angle, and in the fourth quadrant, 360 minus 60 gives me an angle of 300. Now for my final answers, though, they have to be in radian form. So I'm going to take theta equals 60 and theta equals 300, and I'm going to times them each by pi over 180. Okay, you'll do 60 divided by 180 comes out to be pi over 3. 300 divided by 180 becomes 5 pi over 3. And there is a full list of my solutions when you're solving a second-degree trig equation. Okay, so basically it's solving a quadratic, but again, unlike regular quadratics, you're not done when you just get to x. You have to take it a step further to actually solve the trig equation that you get afterwards.